Hello, this video is going to look at how to solve Bernoulli first order differential equations. That's equations that look like this. We know how to solve the left hand side of this sort of equation. We did this in ordinary A level. Here it is, something like that, which we could do with the integrating factor, and we know how to solve the right hand side as our particular integral because it's just a function of x. Now, what's our problem with the Bernoulli equation? Well, I've got some function of x here, but I've got a y as well to some power n. And we're going to solve these using a substitution for y. Okay, so here's my equation I'm going to look at. Here's my general equation. And I'm going to use this substitution here. Z is going to equal y to the 1 minus n. Well, what is this n? Well, that's that n there. And if we do this, it will differentiate down to an equation in Z. We'll translate down to that in differential equation in Z. Left-hand side all looks very neat and tidy. We can integrate that. And what's happened to our right-hand side? Well, that's just become a function of x, and our y to the n has disappeared. So now we could use separation variables or integrating factor to solve it. So let's have a go at an example. Okay, dy by dx plus x y on the left hand side, something we know how to integrate, equals x or y squared. Well, what are we going to do? We're going to do our substitution. We need to work out what n is. Well, the power of y on the left hand side is 2, so n equals 2. So z will equal y to the 1 minus 2, which will be y minus 1, and that's where we get to. Now, in a lot of exam boards, they're just going to give you that substitution. They're going to say, solve this equation using the substitution, z equals 1 over y. They're not going to explain why, but this video will take us through why this works a bit later on. But that's basically where we get our z equals y to the minus 1. Okay, so if we rearrange that, we get y equals z to the minus 1, which I need to get rid of. I need to convert my left-hand side now into a function of z rather than of y. So I need to convert dy by dx into something into z by dx. And using the chain rule, I can do that because dy by dx equals dy by dz times dz by dx. And using this relationship here, y equals z to the minus 1, I can find out what dy by dz is. Well, that's a minus z to the minus 2. Okay, so I've got all the bits I need now to transform my differential equation. So here's my differential equation. What am I going to do? I'm going to replace my dy by dx by this new relationship I just created for in terms of dz by dx. I'm going to replace my y with a z to the minus 1 there, and y squared to z to the minus 1. And if I do that, I get this equation on the next line. So I've got, you'll see that it's still reasonably neat and tidy. It's starting to tidy up, but it's multiplied through in the left-hand term by z to the minus 2 and the right-hand side term by z to the minus 2. Don't really want that, so I'm going to multiply the whole equation by z squared to get rid of that. Yeah, and when I do that, that disappears and that disappears. What happens to this power here? Well, it starts off at z to the minus 1 multiplied by z squared gives us a z power of z, doesn't it? So everything's neat and tidy on the left-hand side. I've got an expression which I know how to integrate. What happened on the right-hand side? Well, I'm just left with x, aren't I? My y squared has disappeared. That's what I wanted to achieve. So now I can solve it, this equation, can't I, using either separation of variables or integrating factor. I'm going to do it with integrating factor because I think that fits better with this sort of setup where I've got something on the right-hand side. Okay, so what's my integrating factor going to be? Well, I've got a plus x here and I've got a negative there, haven't I? So my px here equals minus x, doesn't it? So what does that mean? Well, it means my integrating factor is going to be e to the power the integral of minus x dx, minus x, we're integrating dx, so I get my integrating factor equals e to the minus x squared over 2. Apologies to writing it like that, my software is not great, going for further second power and a power. So what do I do then if I'm using integrating factor? Well, I multiply my whole equation by my integrating factor, and that means that my left hand side will become just the differential of this bracket, integrating factor times z, and I've got a negative sign there. Right hand side is x lots x times the integrating factor, and we can just integrate that equation, can't we? And what do we get? Well, on this side, so on the left hand side, well, we just get the equation, the function of the bracket. On the right hand side, I've got the integral of x e to the minus x squared over 2 integrated dx, which of course we can just see by inspection or by substitution. If you're unsure about it, it would be u equals minus x squared over 2 would be my substitution. I'm going to get that, aren't I? Plus, of course, I've got my constant. Well, this equation still doesn't look very nice, does it? Still doesn't look very nice in that I've got in front of my z, I've got this e to the minus x squared over 2 term. So what I'm going to do, I'm going to multiply through by plus e to the, so e to the plus x squared over 2. There we are, my left and a negative sign, and I get left with z equals, well, my first term here becomes just 1, and my second term here, well, I've just got that power and I've got sign change. So there we have an solution in terms of z, where c is the constant of integration. And now I need to get back to y. Well, I do that by y equals z to the minus 1, which equals 1 over z, doesn't it? And therefore I just sub that back in. So what have I got? Y equals 1 over 1 minus c e to the minus x squared over 2. Yeah, well, c is my integration constant, sorry. So there we have it. That looks pretty straightforward, and it works in all cases. What I am going to look at here quickly is just think about why this works more generally. So if I started off my equation here, and I've got an f of x here on the right hand side, and I've got a y to the power n, I said I'm going to use this substitution generally, y to the 1 minus n, there we go, which if I rearrange it, I get y equals z to the 1 over 1 minus n. Yeah, because y squared, z equals y squared, therefore y equals z to the half. That's the sort of example we might have. And what I do, well, I want to, on the left hand side, I need to get a y by dx. So I'm going to use the chain rule. Again, I've got a relationship between y and z now, so I can find what that differential is. And I'm going to get an equation in dz by dx. Here it is. It's a bit horrible, isn't it? But it simplifies slightly to here. dy by dx is 1 over 1 minus n, and then I've got this power here. It's a bit of an odd one, isn't it? N over 1 minus n. So let's substitute that lot into my differential equation. So I'm going to replace my dy by dx with this, replace my y there with that, and my y there with that. And if I then tidy up a bit and get all my powers sorted out, I get a z to the n over 1 minus n here, my first term, and I also get it on my last term. Here we go. Now I don't really want that. I want to get to somewhere I've got dz by dx on its own. So I'm just going to multiply by the negative power of that. There it is. If I do that, then multiplying by the negative power, I'm going to get z to the naught here and z to the naught there. What happens to this middle term? Well, I had a power here of 1 minus n, 1 over 1 minus n, and I'm multiplying by this power, n over 1 minus n, and it's negative, so you can probably see that combining those, I've got 1 minus n on the numerator now and 1 minus n on the denominator now, so I just get a power of 1. So I get back to z to the 1. So I've just come back to a very neat and simple setup there, haven't I? Left hand side is neat and tidy, all ready for integration with an integration factor, and on the right hand side I've got an f of x with no y power. So there we have it, all ready for integrating factor. I'm not going to do that, but you can see how it would work. So in summary, if you see one of these Bernoulli equations where the left hand side is neat and tidy, all ready for integration, the right hand side has some power of y to the n, then we do our substitution, z equals y to the 1 minus n, and we obtain a nicely well behaved first order differential equation of the sort where the left hand side is all ready for integrating factor and y is just the right hand side, so it's just a function of x. So we've now got, we solve our differential equation of z in x, and then we convert back using our transform, our substitution backwards, and we have our solution. So there you have it. Hope that's of use.